Hey, AP Chem, we are getting into the home stretch of class now, and we are starting Unit 10, which is acids and bases. And this presentation is going to be kind of going over just your bare essentials of what are acids and bases, how do I recognize them, how do they behave in water, that kind of stuff. And then we're going to go deep dive into kind of all the math that goes with calculating things that are related to acids and bases. But today is a light introduction for this stuff. So when we talk about acids and bases, there are kind of two competing definitions for them. Actually, there's three, but in terms of what AP is looking for, they're going to be asking you to compare two definitions, the Arrhenius definition and the Bronsted-Lowry definition. Now, there's something else called the Lewis acid and base definition, but they've removed that from the curriculum, and so we don't have to worry about that right now. So if we're talking about the Arrhenius definition of an acid is kind of the old school version of the explanation for what an acid and a base do. And an acid would be something that releases a hydrogen ion into solution when it hits water. So first of all, an acid doesn't really truly give off or start to show its acidic properties until it becomes an aqueous solution. So if we're talking about something like hydrochloric acid, HCl, nitric acid, which is HNO3, what happens is when those chemicals, when they are originally bonded together, in theory, when they hit the water, they break up into H plus and then something else. So they release an H plus in solution, and that's according to the Arrhenius definition, which is what makes them an acid. And a base then is something that in its chemical formula would have a hydroxide ion, which like sodium hydroxide, potassium hydroxide, when that thing hits the water, then it releases an OH minus, and then that makes the solution basic. So in general, acids have higher than normal concentrations of H plus ions, and bases have higher than normal concentrations of OH minus ions, okay? But the Arrhenius definition says that that chemical has to have an H released for an acid, and it releases an OH from the formula if it's a base. That definition works for a lot of chemicals, but there are many other substances that are basic or acidic, and especially are bases that don't necessarily follow those rules. So along comes the Bronsted-Lowry definition. And in the Bronsted-Lowry definition, it has to do specifically with acids and bases, figuring out which ones they are by tracking your hydrogen ions, okay? So in the Bronsted-Lowry of a definition, an acid donates an H plus in a reaction. So when we look at what's going on, the acid's going to lose an H plus from its chemical structure. And that is pretty much identical to what happens with our Arrhenius definition. But the base definition broadens and really opens things up, and it helps a lot. In the Bronsted-Lowry definition, bases receive hydrogen ions in a reaction. They don't need to have an OH in their formula, but by their nature, they will make the OH minus concentration go up because they can take an H plus. And that might not make a lot of sense right now, but we'll go through a couple examples and hopefully clear things up a little bit. When we talk about the Bronsted-Lowry definition, there are a couple of other terms that you need to know. One of them is the conjugate base. So the conjugate base is what is left over after the hydrogen leaves your acid. So it's kind of the stuff that is there. And then the conjugate acid is what's made when the H plus joins the base. So if we think about the base as something that's taking the hydrogen, the combination of the hydrogen and your original base, that is going to be your conjugate acid. And like I said, this maybe doesn't make a whole heck of a lot of sense till we see some examples. So here we go. This is the dissociation of hydrochloric acid in water. So if I take hydrochloric acid and I put it into water, it is going to dissociate or break up a little bit. And when it does, it gets together with water and it reacts and creates Cl minus and H3O plus. Now, this is the Bronsted-Lowry kind of definition of this. If we're talking about the Arrhenius definition, it's just HCl, and then it breaks up into H plus and Cl minus. So it's a little bit different depending on the definition, but I like to use the Bronsted-Lowry definition of an acid or base because it covers tons of different substances. So the trick is with this to watch what's happening with the hydrogen. Something's going to lose a hydrogen and something's going to gain a hydrogen, and that's going to let us know the identity of all of our things here. So you can kind of see that the H in the HCl leaves and goes and connects to the H2O. And we know that by looking at what we have for our products here. So if we look at our products, I've got a Cl minus that's left over. So we're missing that original H. And now the H2O has an H added to its formula as well as a plus. Okay, so it becomes H3O plus. As far as labeling these things go, HCl is our acid because it lost the hydrogen, and that makes H2O our base because it is taking the hydrogen on. And this is kind of a weird thing where water you don't think of being acidic or basic, but by the Bronsted-Lowry definition, in this case, H2O is acting as a base because it's taking that H from the hydrochloric acid. Now, the real question is, what are these guys down here? Okay, so when we think about them, our products are going to be our conjugates. It's just an issue of deciding what becomes what. And in this case, the acid turns into the conjugate base. So the Cl minus, that is the conjugate base, and then the H3O plus is the conjugate acid. And so when I am talking about what is going to affect my pH, it's an increase in H plus concentration, right? That's what I just said before. Here's the deal. The H3O plus in our equation here, that is essentially another way of writing H plus. This guy here has the name the hydronium ion. And the hydronium ion is just a fancy way of writing H plus. There's some other kind of chemical reactions that are going on, and I'll get into that when we talk about pH and where this H3O plus is coming from. But essentially what happens is when an acid dissolves in water, it bumps up this hydronium concentration, and that's what makes it acidic. Okay, here's another one. It's NH3 plus H2O, and that turns into NH4 plus and OH minus. Okay, so if we look at this, in this case, we follow the hydrogens to see what's going on. If we look at reactant to product, okay, we can see that our H2O is losing a hydrogen ion, an H plus, to the NH3, okay? So in this case, since the H2O is losing it and the NH3 is gaining it, it means that NH3 is our base and H2O is our acid, okay? And I said before that acids have a higher than normal H plus concentration and bases have a higher than normal OH minus concentration. Well, if you look initially at NH3, you would say to yourself, I don't see any OH. How could this be basic? What happens is it will take the hydrogen from the water and then it will leave the water as an OH minus. So even though this here, ammonia, doesn't have an OH in its formula, by the way it behaves, it'll take that H from the H2O and then it turns it into an OH minus, making that concentration go up. Okay. If we think about the names of the partners, NH4 plus is the conjugate acid because our base turns into our conjugate acid, and then our OH minus is our conjugate base. Now, NH3 and NH4 plus are what we call a conjugate acid-base pair. So a acid-base pair, a conjugate acid-base pair, what they are the original kind of parent base and then the baby conjugate acid, or the original parent acid and the baby conjugate base. So think about what this is and what it turns into. That is a pair. So H2O and OH minus are also a pair as well. In our previous equation, it would be HCl and Cl minus, and then H2O and H3O plus. So those are called conjugate acid-base pairs. Sometimes you'll be asked to identify those. Okay, so in the case of water, you may have noticed that it is acid in one reaction and base in another. And there are some substances that can do that. And if that's the case, they have the name amphoteric. Ampho means kind of both. So if we have amphoteric, it means that that substance can be an acid or a base. And the reason it can be an acid or a base is because it can lose a hydrogen, or it can take on a hydrogen ion in both points, depending on what it's with. So there are some substances that are amphoteric, and H2O happens to be the most common one of them because it can take an extra hydrogen and become H3O+, but it can also lose one and become OH-. All right, when we are talking about an acid or a base, sometimes you can take a look at the chemical formula and there are things that are going to tip you off about if it's an acid or a base. For an acid, the easiest way to identify them is that the formula starts with a hydrogen ion. So if you see H, blah, 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 it's probably an acid. In the other case for acids, if the formula ends in COOH, that is called a carboxylic acid, and it's a double bonded oxygen to a carbon, and then an oxygen and a hydrogen coming off of that. So you will see that sometimes. The biggest one of those is acetic acid, vinegar. And so you'll see it ending at the end there. For bases, and I'm sorry my face is covering this up here. Let me move my head up for just a second. Ooh, let's see if I can screw this up. Aha. Okay. So for bases, the formula is going to end in OH-. That's the easiest one to spot. All of your hydroxides are basic. But another thing that you can see is if the formula ends in NH something. Specifically, we look for NH2s and NH3s, and those usually tip us off that we're going to have something that can take on an extra hydrogen. Those nitrogens can take on up to 4 hydrogens total comfortably, and so they work really well as acids or bases. All right, I'll move my head back down. Okay, some properties of acids. We will get way into pH and how you calculate that in another section here. But just for now, you should know that acids have a pH that's lower than 7. 7 is usually considered neutral. Acids are sour tasting. When you eat them, they have properties that when they hit your taste buds give it a sour flavor, and even your pure acids like HCl and sulfuric acid just straight up taste sour. It's not like they're sweet, they are just literally sour, and that's it. And we say that they're corrosive. So acids, if they're at a high enough concentration, can potentially react with metals. And when they do that, they will react with the metal and they will also produce hydrogen gas. So they will actually dissolve metals if the concentration is high enough and if they're exposed to it long enough. And acids will set off pain receptors. So if you get an acid on your skin in a high enough concentration, if it sits there, it'll start to trigger off your pain receptors. You'll feel it. If you ever get like acid into a cut or something like that, you'll know it because it triggers those pain receptors. So you know you're getting burned while you do that. On the other side of things, bases are pHs above 7. So if you see something that's got a pH that's higher than 7, it's going to be basic. Bases tend to be bitter tasting. So if acids are sour, bases are bitter. And bases are slippery to the touch. So slippery to the touch, it's kind of a cool reaction that happens when you get a base on your fingers. What happens is it starts to kind of react with the oils on your fingers and it dissolves those oils and they start a reaction called the saponification reaction. That just basically means that you're kind of being turned into human soap. So it feels slippery because you're slowly dissolving. Interestingly, it does not trigger your pain receptors at all. So if you get a base on your fingers, it can actually do damage to you, but you don't feel it, which in theory, you're like, yay, I'm not in pain, but also problem because you don't know it's reacting on there. So if you get a base like sodium hydroxide on your fingers, it's going to feel real slippery to the touch, and that's because you're kind of slowly dissolving your fingers. Yikes. Okay. And then other terms to talk and describe about bases is you'll hear the term caustic thrown around, and caustic just means it's going to potentially dissolve things as well, but it's talking about a base versus an acid. Acids are corrosive, bases are caustic. And you also hear the term alkaline thrown around. So alkaline is just another fancy word for basic. All right. So this is kind of the nuts and bolts of acids and bases. The big thing you need to know from this section is that an acid makes the H plus concentration go up, or H3O plus. Bases make OH minus go up. And then you need to know how to identify conjugate acids and bases and predict what's going on. So take a look at those problems, see on your homework assignment, see if you have any questions, and then we will chat about 10.2. All right, good luck.